Good morning, students. Yesterday we discussed projection operator and its properties, and today we will discuss null space lemma. So what is the statement of this lemma? The orthogonal complement of a closed subspace Y of a Hilbert space H is the null space of the orthogonal projection P of H onto Y. Means we have to prove that the null space of P is equal to the orthogonal complement of Y, which is Y complement. We have to prove this. So in order to prove this, we will use projection theorem and the definition of projection operator. Now because Y is closed subspace of Hilbert space H, so we can use projection theorem. So by projection theorem, H can be written as the direct sum of Y and its orthogonal complement. So H is equal to Y direct sum Y complement. So by definition of direct sum, it means we can say that for every X belonging to H, we have a unique representation in the form of sum, in which one element is taken from Y and this element is taken from the orthogonal complement of Y. Now we define the projection operator. By definition, projection is defined on the Hilbert space H to Y, defined by if we take an element X from H, then the image of X, that will be an element of Y, which we have denoted by Y. So P of X is equal to Y. This defines projection operator, and we already discussed this as onto mapping from H to Y. Now we have to prove that null space of P is equal to the orthogonal complement of Y. So in order to prove this, now what is null space of P? Null space contains all those elements of Hilbert space H whose image under the mapping P, that is 0. Now we have to prove that null space of P is equal to Y complement. It means we will have to prove that null space of P is contained in Y complement and Y complement is contained in null space of P. So first of all, we will prove this part. We have to prove that null space of P is contained in Y complement. So let us take an arbitrary element from null space of P. We have taken X belonging to null space of P. Now by definition of null space, the image of this element X under the mapping P, that will be 0. Now by definition, P of X is Y. So from here we get Y is equal to 0. Now X is equal to Y plus Z. Now Y is 0. So X will be is equal to Z. But Z is an element of the orthogonal complement of Y. It means Z belongs to Y complement, and because X is equal to Z, so X will also belong to Y complement. So we had taken X from NP and we have proved that X belongs to Y complement. So we have proved that null space of P is contained in Y complement. Now to prove the converse part, now we'll prove that Y complement is contained in null space of P. So let us take an element X belonging to Y complement. Now X can be written as 0 plus X. Now because this is the element of Y, this is the element of Y complement, so it means X belongs to Y plus Y complement. Y plus Y complement, because H is the direct sum of Y and Y complement, so we can say X belongs to H. Now we have to prove that X belongs to null space of P. So we will have to prove that the image of X under the mapping P is 0. Now let us find the image of X under P. Now image of X under P. Now X can be written as 0 plus X. Now we again use the definition of projection. By definition of projection, P of X. X is Y plus Z. So image of Y plus Z is Y. So this is Y, this is Z. So image of Y plus Z is equal to Y, means P of X is equal to 0. So by definition, X belongs to null space of P. So we had taken element from Y complement and that is going into the null space of P. It means Y complement is contained in null space of P. Combining these two equations, we get Y complement is equal to null space of P. Thus we have proved that orthogonal complement of the closed subspace Y of the Hilbert space H is the null space of the orthogonal projection P. So this was the lemma. Now next is the topic, what is annihilators. So definition, what is annihilator? Annihilator of a non-empty set in an inner product space X is defined by the annihilator of M is denoted by this symbol. So annihilator of M is the set of all those elements of the inner product space X which are orthogonal to M. So the set of all those elements of X which are orthogonal to M, that forms annihilator of M. By definition, because X is orthogonal to M means X has its inner product with every element of M as 0. So we can say that if X belongs to M annihilator, then inner product of X with every element of M will be 0. So this condition is true from both sides. If X belongs to M complement, this condition holds, and if this condition holds, X belongs to M annihilator. Now next is the property of this annihilator. We will prove that M annihilator is subspace of the inner product space X. So in order to prove this, according to the definition of subspace, we will have to take two elements from annihilator of M and two scalars alpha beta from the field of scalars, and we will prove that alpha X plus beta Y belongs to annihilator of M. So in order to prove this, by definition of annihilator, annihilator में वो सभी elements आते हैं which are orthogonal to M. So in order to prove this is orthogonal to M, we will have to show that its inner product with every element of M is 0. So we will have to prove this. So let us consider the inner product of alpha X plus beta Y with Z. Now by using the properties of inner product, linearity property, so by that property this can be written as inner product of alpha X with Z plus inner product of beta Y with Z. Now we can take alpha outside by the properties of inner product. So this can be written as alpha into inner product of X with Z plus beta into inner product of Y with Z. Now we can see that X and Y belongs to annihilator of M. So by definition of annihilator, if X belongs to annihilator of M, X will be orthogonal to M. It means inner product of X with every element of M will be 0. So inner product of X with Z will be 0. In the same way, Y belongs to annihilator of M. So inner product of Y with every element of M, that will be 0. So these two terms becomes 0. So we get inner product of alpha X plus beta Y with Z is equal to 0. So we can say that by definition alpha X plus beta Y belongs to annihilator of M. So we have proved the property of annihilator of M, that it is a subspace of the inner product space X. Now next property is annihilator of M is closed, and we know that a set is closed if and only if its closure is the set itself. So we will have to prove that the closure of annihilator of M is equal to annihilator of M. If two sets are to be proved equal, then we will prove their containment into each other. So we will have to prove that this set is contained in this and this set is contained in this. And we know that every set is always contained in its closure. So annihilator of M will be contained in its closure. Now we'll prove the converse part. We will prove that the closure of annihilator of M is contained in annihilator of M. So let us take an element from the closure of annihilator of M. By definition of closure, by definition it means we can say that because X belongs to closure, so X is closure point of M annihilator. So by definition there exists a sequence of the points in annihilator of M which will converge to X. Now we have to prove that X belongs to annihilator of M. Now by definition it means we will have to prove that the inner product of X with every element of M vanishes. So let us consider an arbitrary element from M. We have taken that element as V. Now let us find the inner product of X with V. Now what is X? That is the limit of the sequence Xn. So substituting the value of X here, this will become inner product of limit of Xn with V. Now because we know that inner product is a continuous function, so the limit can be taken outside of the inner product. So this will become limit of inner product of Xn with V. Now because Xn is a sequence of points in annihilator of M, and by definition of annihilator, so inner product of Xn with every element of M, that will be 0. So this will become 0. So we have obtained inner product of X with V is equal to 0. And this is true for every element of M. So we can say that X is orthogonal to M. By definition, if X is orthogonal to M, so it means X belongs to annihilator of M. So we had taken an element from the closure of annihilator, and we have proved that it is contained in, it belongs to annihilator of M. So we have proved the condition from both sides. Combining the equations 1 and 2, we have obtained the closure of annihilator of M is same as the annihilator. So the set is closed. So this is the property that annihilator is closed. Now the next property is, if M is a non-empty subset of an inner product space X, then in general M is contained in M double complement, means annihilator of M. So we have to prove this property. In order to prove this, let us take an element X belonging to M. Now by definition, because the elements of M and M annihilator, they are orthogonal to each other. So if we take an element X from M, then its inner product with every element of annihilator, that will be 0. So from here, inner product of X with V will be 0. And from here we can say that inner product of X, V with X, that will also be 0. It means we can say that X is orthogonal to annihilator of M. And by definition, if X is orthogonal to annihilator of M, X will belong to M double complement. So we have taken X from M, and that is belonging to this set. So we can say that M is contained in M double complement. And the reverse condition is also true if we have a closed subspace. If M will be closed, then M double complement will also be contained in M, and we will prove this property tomorrow.